Welcome to the Bologna classes. In this session, we will see few NCERT numerical and other numericals on the basis of interference of light. Let us solve first numerical. A monochromatic light of wavelength 589 nanometer is incident from air on water surface. What are the wavelength, frequency and speed of reflected and refracted light? Refractive index of water is 1.33. See here. Actually, all phenomena, whatever reflection, refraction, all the phenomena that can be explained by using wave theory of Huygens wave theory of light. In detail, we can explain interference of light using Huygens wave theory of light. On that basis, let us see what is first numerical. A light, monochromatic wavelength of light is given. Shall I go for solution? Wavelength of light. How much? Wavelength of light lambda is equal to 589 nanometer. Nano mean 10 raised to minus 9 nanometer. Incident from air on water surface. Ray of light incident on water. What is wavelength, frequency and speed? Wavelength, frequency and speed during reflection and refraction of light. Refractive index of water given. Refractive index of water is how much? Refractive index of water that equal to 1.33 given. See here. We know that when ray of light reflected, the speed of the light, wavelength of the light and frequency of the light always remains same. Speed of the light, wavelength of the light and frequency of the light always remains same during reflection of light. During reflection of the light doesn't changes anything. See here. What we know, the speed of the light in air. How much? Speed of the light in the air can be represented 3 into 10 raised to 8 meter per second. The speed of light doesn't changes during reflection of light. Then during reflection of the light, how much frequency is there and how much wavelength is there? See here. During reflection of the light, I can say during reflection of the light you can go directly. See here, wavelength of light given. Wavelength of light how much during reflection? See here, wavelength of the light lambda is equal to 589. This remains same always. This remains same. Frequency, then you can calculate frequency. See given, what is speed of light here? Speed of light is equal to 3 into 10 raised to 8 meter per second. But we need frequency. We need frequency during reflection. See here. Again, from this you can calculate. How to take the frequency from this? C is equal to F into lambda. Or what is F? F is equal to C divided by lambda. C is equal to 3 into 10 raised to 8 lambda given 589 into 10 raised to minus 9. So from this you can calculate frequency. Of what order? Frequency you can calculate this frequency F is equal to 5.09 into 10 to 14 Hz. This is frequency of the light during reflection, speed of light during reflection and wavelength of light during reflection. Then again we will see during refraction. See, during refraction means the phenomenon of bending of light or phenomenon of change in path of light when ray of light travels from one medium to another medium. The ray of light, it goes from air to water, so that here wavelength changes, speed changes, but frequency remains same. During refraction, which physical quantity remains same? During refraction, the frequency of the light remains same, because frequency is the characteristic property of the source, but not characteristic property of the medium. So frequency remains same during reflection and refraction. Now, from this, second one you can calculate how to take during reflection of light and during refraction of light. See here. Now, let us go during refraction. I need to calculate. See here. During refraction of light, initially we will calculate how much speed is available. See here. I can define refractive index in this way. Ratio of speed of light in two medium. Ratio of speed of light in two medium, that I can call directly, that I can call refractive index. See here, how to define refractive index? The ratio of speed of light in two medium. Refractive index of water with respect to air. Let us consider. C represents speed of light in air, V represents speed of light in water. Then from this, what value we are getting? V is equal to how much? V is equal to C divided by mu. V is equal to C is equal to 3 into 10 raised to 8 meter per second and mu is equal to 1.33. So the speed of light from this you can calculate. Around this value it will come. V is equal to 2.26 into 10 raised to 8 meter per second. Are you following this? This is what? Speed. But frequency during refraction remains same. How much frequency was available? This much frequency. This frequency during refraction remains same. How much frequency we are getting? Frequency of the order 5.09 into 10 raised to 14 Hz is available. This frequency always remains same. Then what about wavelength? How to calculate wavelength? See here. I can define like this. Refract index. In what way? Refract index shall I define here? Look at me. This is what frequency during refraction. Then wavelength during refraction will calculate. See here. This second right. In what way? Mu is equal to how much? Mu is equal to C divided by V. What is C? C is equal to F into lambda. And V is equal to what value? F into lambda dash. Lambda represents wavelength of light in air. Lambda dash represents wavelength of light in water. So that from this what we are calling again? See here, from this F and F can cancel because during refraction and refraction frequency of the light remains same. Then from this again what we are taking? Mu is equal to how much? Mu is equal to lambda divided by lambda dash, or else what is lambda dash from this? Lambda dash is equal to lambda divided by mu. Lambda how much? Already given 589. 589 into 10 raised to minus 9 divided by how much? Mu is equal to 1.33. Then from this wavelength around we are getting wavelength of the order lambda dash is equal to 444 nanometer. Nano mean 10 raised to minus 9 meter. This is wavelength during refraction, frequency during refraction, speed during refraction. During reflection, this is wavelength, this is speed, and this is frequency. Copy it. Let us move for next numerical. Okay. Shall I move the next numerical? I can take numerical. Look at me. What has given the numerical? A monochromatic light of wavelength 589 incident from air on water surface. Sorry. Let us go. Numerical number 2. See here. In Young's double slit experiment, slits are separated by 0.28 millimeter. Distance between slit given, that is 0.28 millimeter. And the screen is placed 1.4 meter away from the screen. From the slit. Distance between slit and screen given 1.4 meter. The distance between central bright fringe and fourth fringe is measured to be 1.2 centimeter. Distance from central bright fringe to fourth, n is equal to 4. Determine wavelength of light used in experiment. Determine wavelength of light used in experiment. Look at me. In Young's double slit experiment, slits are separated. Shall I go solution of it? Look at me. I can take solution of this numerical. See here. In Young's double slit experiment, slits small d is there. Small d how much? 0.28 millimeter. 0.28 into 10 raised to minus 3 meter. And the screen placed 1.4 meter away. That is capital D given. 1.4 meter away. The distance between central bright fringe and fourth fringe is observed to be 1.2 centimeter. See here. Here x value given. X value is equal to 1.2 centimeter. That is converted into meter. 1.2 into 10 raised to minus 2 meter. For what? Distance from central to fourth. N is equal to 4. N is equal to 4. Wavelength of light used in experiment. I need lambda. See here. In Young's double slit experiment, we obtain expression for fringe width. What was it is? See here. X is equal to how much? X is equal to n into lambda capital D divided by small d. Are you following this? X is what? Distance of the fringe width from central bright fringe. N is equal to number of fringes observed. Lambda wavelength of light used. Capital D, distance between slit and screen. Small d, distance between two slits. See here. All values are given. What we need? What is wavelength of light used? From this, shall I take wavelength of light used? Lambda is equal to x into small d divided by n into capital D. Write on this. Lambda is equal to n into x divided by n into capital D. Lambda x given 1.2 into 10 raised to minus 2. 10 raised to minus 2. Small d 0.28 millimeter. 0.28 millimeter divided by n. N is equal to 4. Capital D, how much? 1.4. If we calculate all these values, lambda will get around will get 600 into 10 raised to minus 9 meter. Or else directly I can write of the order, this is minus 9 mean nano, so that I can write lambda is equal to 600 nanometer. This is wavelength of light used in Young's double slit experiment. This is solution of it. Copy it. Let us move for the next numerical. See here. Shall I remove it? Okay. Let us move the next numerical. See here. Numerical number 3. A beam of light consists of two wavelengths, 650 nanometer and 520 nanometer, is used to obtain interference fringe in Young's double slit experiment. A beam of light consists of two wavelengths, one is lambda 1 and lambda 2, that is used in Young's double slit experiment to obtain interference pattern. Option 1, what is given? Find the distance between third bright fringe on the screen from central maxima for the wavelength of light 650 nanometer. Only we will solve option A, later we will go for the option 2. Look at me. See here. What it is? A beam of light consists of two wavelengths. Shall I go for solution of it? Look at me. Beam of light consists of two wavelengths, 650 nanometer. 650 nanometer and 520 nanometer. Lambda 2. 520 nanometer. Used in Young's double slit experiment. What we need? Option A. Find the distance of third bright fringe. Find the distance of third bright fringe. N is equal to 3. N is equal to 3. For what wavelength? For 650. I mean for lambda 1. That we'll see. Look at me. Again we know that this x is equal to how much? X is equal to n into lambda capital D divided by small d. In this numerical, capital D and small d are not given. Take it up the solid. They kept capital D and small d are the same. See here. What we need again? X is equal to how much? N is given. N is equal to third bright fringe. N is equal to 3. This is lambda 1 because 650 is lambda 1. 3 into lambda 1, 650 into 10 raised to minus 9 into capital D divided by small d. Capital D divided by small d. Correct. Then from this again we will take the value. How much? This is 1950 into 10 raised to minus 9 capital D divided by small d. Because capital D and small d value is not given. So keep it upside. 1960. See here. Now, option B will read. What is given option B? What is the least distance from central maxima where bright fringes to both wavelength can coincide? What is the least distance from central maxima where bright fringe due to both wavelength can coincide? Both wavelength can coincide. See here. Now we'll see this numerical. See here two wavelengths are given, lambda 1 and lambda 2. For lambda 1 and lambda 2, two values of n are available. At some other fringe width, both wavelengths are coincide. The distance we need from this. I mean, see here. What is given? Look at me. Here x value given. How much x value? X value is equal to n into lambda capital D divided by small d. Capital D divided by small d. Let us call this is equation number 1. At some other distance where lambda 1 and lambda 2 are coincide. For what fringe width shall I take here? Look at me. Actually x dash is equal to, for this order both wavelength can coincide. Look at me. I can take this as lambda 2. See here. Shall I take here directly? I can take this value is for lambda 1. Lambda 2 I will take for this directly. And x dash is equal to where it is coincide? It is coincide exactly at lambda 1 capital D divided by small d. Look at me. At this fringe, at this wavelength, both ray applied with a different wavelength can coincide. That distance we need. See here. From this what you obtain? If the coincides mean, directly I can take both the wavelength are coinciding, mean here x dash must be equal to x value. Coinciding mean whatever both fringes they must be overlap each other. I mean both wavelengths are coinciding mean at some other distance both wavelengths are coinciding. For this condition x dash is equal to x value. Then see here. We need from this. I can take this as x dash. For my reference I can take okay, no matter you can take directly. See here. X dash is equal to what value are taken? N minus 1 into lambda 1 capital D divided by small d is equal to x value how much? N into lambda 2 capital D divided by small d. Here what values are? Small d cancel, capital D get cancel. What is remaining from this? N minus 1 into lambda 1 is equal to n into lambda 2. Right around this. Then again from this, if you solve n minus 1, keep it up same, lambda 1 given how much? That is 650 nanometer is equal to, this is how much? 520 nanometer into how much? N value. Solve this, what value we are getting? N is equal to 5. N is equal to 5. I mean at this order both wavelengths are coincide. At this order what is the distance that we need? See here, already we have taken x and x dash already I taken. X dash for lambda 1 I taken and x for lambda 2 I taken. Look at me then. Then at some other distance, at what distance is asking? I mean this fringe width. To this fringe width I need what is the distance. Again we will take. See here. What we know that again I can take x double dash is equal to n into lambda. N into lambda 2 or lambda 1 I can take. D dash dot d divided by small d. Right around this. For what wavelength we will take directly? Directly I can take for this one lambda 2 I will take because it is coinciding at some other wavelength, I can take it as lambda 2. I can take this is what value x double dash. Then here n given how much? N is equal to, that is 5. 5 is come because at this order both wavelengths coincide. Lambda 2 already given, that is 520 nanometer. Nano mean 10 raised to minus 9. Capital D divided by small d. Capital D divided by small d not given the values. Right. Then again from this you can take like this. X double dash is equal to 2600 into 10 raised to minus 9. Capital D divided by small d. Here these values are not given. So this is the distance. This is the distance and this is the fringe width where both wavelengths are coincide. Copy it. Let us move for the next numerical. Now, numerical number 3 this is. Now let us go numerical number 4. Okay. Shall I take the numerical number 4? See here. Question is what he has given. In a double slit experiment, angular fringe width are found to be 0.2 degree Angular fringe width is found to be 0.2 degree. On a screen placed 1 meter away, distance between slit and screen is given, that is 1 meter. What is the angular width if the entire experiment apparatus is immersed in water? Refractive index of water is 4/3. See here. Initially we will see how arrangement of Young's double slit experiment looks like. See here. What are taken in case of Young's double slit experiment? This is nothing but two slits. So this is slit 1 and slit 2 separated. I can take this is nothing but slit 1 and this is slit 2 and this is the screen. This is the screen right around. Distance between two slit and screen, that is given by what we call capital D. Distance between two slits, that is represented by small d. Right around this, how it is? Let us take actually from this you can take a ray of light comes meeting at some other point. Again the ray of light that is meeting at some other point. At P point both rays of lights are meeting. This is the direction. Right around. This is the direction. Are you following this? From this object, look at me. What is given in the question? In a Young's double slit experiment, angular fringe width is found to be 0.2 degree. What is angular fringe width? That we will see. Look at me. In case of Young's double slit experiment, if we draw a perpendicular line, say this is nothing but one perpendicular line drawn, already you have seen. So I can take this is SN perpendicular. SN perpendicular, look at me. Then this is some angle made. This angle made I can call theta. This theta what are calling? That theta we are calling angular fringe width. Angular fringe width. See here in the diagram already we know that S2P minus S1P, that is nothing but path difference. Which equal to path difference? So this is equal to path difference. That we are calling del x. That we are calling what? Del x. Look at here. How to define here? What is given here? Angle given. Angle how much? Angular fringe width. Angular fringe width. Angular fringe width theta is equal to what value? Theta is equal to 0.2 degree. Then for what wavelength? For wavelength of the light is 600 nanometer. 600 nanometer. Then what is new angular fringe width if it is immersed in water? Refractive index of water is 1.33. Refractive index of water is 1.33. See here. To understand this, we know refractive index. In what way I can define? Refractive index either I can define ratio of speed of light into medium or ratio of wavelength of light into medium. Similar, the ratio of angular fringe width into medium. In air, how much angular fringe width is available? 0.2 degree available. Right? For what wavelength? For this wavelength. Then in water, how much angular fringe width available? Theta dash available. How can define refractive index? Refractive index I can define ratio of speed of light into medium, or refractive index I can define ratio of wavelength of light into medium, or else refractive index I can define a ratio of angular fringe width in air to angular fringe width in medium. In water how much available? Theta dash available. In air how much available? Theta available. You can solve very easily this numerical. See here. Then directly I can define refractive index in what way? Refractive index is equal to ratio of angular fringe width into medium. See here. Theta dash is equal to theta divided by mu. Theta is equal to 0.2 degree. Refractive index is 1.33. So from this what you observe theta dash, that is 0.15 degree. Angular fringe width in water is decreased. As refractive index increases gradually, the width of the interference pattern that will decrease. I mean width of the bright band and width of dark band will gradually decrease. So remember this point. And this is what solution of this numerical. Copy it. Let us move for next numerical. Look at. Let us go for next numerical. Okay. See here. Next question. Question is very simple again. What we know? In a double slit experiment using wavelength of light 600 nanometer, Angular fringe width formed on a distance of point from the screen is 0.1 degree. I mean width of the interference pattern 0.1 degree. What is spacing between two slits? See here. Let us go solution of it. What are given values we will write initially, then we will see later on the solution of it. Look at me. In Young's double slit experiment, wavelength of light used, lambda given 600 nanometer. 600 nanometer. Angular fringe width theta given how much? 0.1 degree. What the distance between spacing between the slits? Small d I need. Very simple. Again we will go for expression for fringe width. How the diagram looks like? See here. This is what the two slits. Are you following? I mention it as S1 and this slit as S2. This is screen. This is screen. So one ray of light, that is S1P meeting at some other point and S2P meeting at some other point. So let us take this point as P. Then from this midpoint I taken this is the distance. So I can take this is O point. This is what value? D point I taken. Then this is some outline again. Again we know path difference. See here. Actually this S1 and S2 distance between two slit, how it is represent? This is represented by small d. I need path difference. If you need the path difference, what we will do? I can draw a perpendicular line. See here. Sn perpendicular to what value? S to P. Then what we are taking? This angle we are calling angular fringe width. This is angular fringe width. Then S2P minus S1P, that represent path difference, which is equal to path difference. S2N is equal to path difference del x. Now, what I need? Distance between spacing. I mean distance between two slits I need to solve this. What we will do? Look at me. Now here one triangle looks like in this figure. Which is the triangle? Triangle S1 S2N is the triangle. In this triangle shall I take sin theta? Sin theta is equal to opposite S2N divided by S1 S2. The triangle. But whatever sine of angle of incident, whatever sine of angle of refraction during optics or during reflection, refraction of light, that assumed to be very very small. So theta is very very small. Sin theta is equal to theta, that we are calling angular fringe width. Theta is equal to S2N, that is del x. S2N is equal to what value? Del x, or else del x is equal to what n lambda. Then later S1 S2 is equal to small d. But path difference for bright fringe, what is asking? Is asking angular fringe width for anyone you can take. For directly I can take this del x is equal to n lambda for bright fringe, n lambda whole divided by this value, because for a bright fringe what is path difference? That is n lambda. N is equal to 1 height because n is not given, order is not given. Wherever order is not given, shall I take directly? For order not given, n is equal to 1 I will take. If n is equal to 1, what about this formula again? Theta is equal to lambda divided by small d. Then from this, what you obtain? From this you can take directly d is equal to lambda divided by theta. Lambda already given, that is in meter. See here, how to put then? D is equal to lambda is how much? 600 into 10 raised to minus 9. Theta is given in terms of degree, so let us convert into radian. 0.1 into 5 divided by 18. 5 divided by 180. 5 divided by 180. 180 goes upside. 5 value 3.142. So 600 into 10 raised to minus 9 into 180 divided by 0.1, 5 value 3.142. This is what value? 3.142. Then again from this we will take the of the value d is equal to 3.44 into 10 raised to minus 4 meter, or else how to write? Distance between two slits, that is of the order 0.344 into 10 raised to minus 3 meter. Minus 3 mean milli. Shall I directly this value? This is distance between two slits. This is angular fringe width and this is distance between two slits, small d value. Copy it. So let us go for next numerical. Okay. Let us take next numerical. What it is? A parallel beam of light of wavelength 500 nanometer falls on a narrow slit, resulting diffraction pattern is observed on the screen. So this is belongs to diffraction. We will solve in the next session. So because this numerical is belongs to diffraction, let us go. One more numerical we will see. See here. What is numerical? In an Young's double slit experiment, the distance between the slits is 1 mm. Distance between, they should be slits, they should be as well. Distance between slits is 1 mm. The fringe width is found to be 0.6 mm. Fringe width is found to be 0.6 mm. When screen is moving through a distance of 0.25 meter, away from the plane of the slits, the fringe width becomes 0.75 mm. Find the wavelength of light used. Find wavelength of light used. See here, what is given? In a Young's double slit experiment, distance between slits. Shall I take solution of it? Young's double slit experiment, distance between slits is given, d is equal to 1 mm. 1 millimeter. 1 millimeter is found to be x value given. X value how much? 0.6 mm. 0.6 mm. Right. When the screen is moving with the distance of what value? 0.25 meter. Look at me. I can take directly this value as what value? D dash is equal to what value? 0.25. D dash is equal to directly increase mean how much? That is d plus how much? 0.25. D plus 0.25. The fringe width is found to be 0.75. When distance is moving by this much, now the fringe width becomes x dash. X dash is equal to what value? 0.75 mm. That is 0.75 to 32 minus 3 meter. What is wavelength of light used? What is wavelength of light used? See here. Question is very simple. In a Young's double slit experiment, distance between two slits is found to be 1 mm. Small d. The angular fringe width is found to be 0.6 mm. Initially we will say angular fringe width. How much angular fringe width? 0.6 mm. We know relation. X is equal to how much? X is equal to n into lambda capital D divided by small d. I don't know how much capital D has given. Right. Now shall I take? I can take this as equation number 1. Now for what value? I can take this is what value? x1. Now I can take this as x2. Right. Then if the screen is moved through a distance of 0.25 away from the plane slit, the fringe width becomes 0.75 mm. See here. When distance moving, distance mean I can take it is x2. X2 is equal to n into lambda. Distance is how much distance? That is the d plus 0.25 whole divided by capital D. Right around this. Now I can take this is what value? Equation 2. If the screen is moving this much, this fringe width will become like this. How much has given? That I can take this is what value? X1 I will take and this is x2 I will take because I taken x1. I need wavelength of light. To calculate wavelength of light, simply make it x2 minus x1. Subtract equation 2 from equation 1. See here. How to need? X is equal to x2 minus x1 will take. X2 minus x1. See here. X2 minus x1 should directly. Shall I solve here? X2 minus x1 how to solve? X2 is what value? That is 0.75 mm. 0.75 mm. X1 how much? 0.6 millimeter. 0.75 mm. 0.6 mm is equal to x2 what is x2 value? N into lambda capital D plus 0.25 whole divided by small d. X1 how much? N into capital D small d, sorry, n into lambda capital D divided by small d. Here what are common values? N is common, lambda is common, small d is common. See here 0.75 minus 0.6, how much it is? That is 0.15 into 10 raised to minus 3, because minus 3 is common. Here what are common values? See here n into lambda small d is common, so what it is remaining? D plus 0.25 minus d. Are you following this? This value get cancelled. Then what is remaining? 0.15 into 10 raised to minus 3 is equal to, n is not given, so keep it up 1. Lambda I need to calculate that value. Lambda divided by small d, because n is not given. Which order is not given? Then that should be equal to 1 value. Then I need from this d. How to calculate d value? See here, d is equal to lambda divided by 0.15 into 10 raised to how much? Sorry. I need lambda from this. D given already. See here, lambda. How to calculate lambda from this? Lambda is equal to 0.15 into 10 raised to minus 3 into small d. D given 1 millimeter. Then again this lambda will take, lambda is equal to 0.15 into 10 raised to minus 3 into how much? 1 mm. 1 into 10 raised to minus 3. So if you solve all the values, then around what value we are getting? So this is of the order, see here, calculation in the single, look at me, follow calculation once again. Here 0.25 is available, look at me, see here 0.25 remaining into how much? 0.25. 1 into lambda, n is equal to 1, lambda is, I don't know that value, lambda into 0.25, lambda is equal to, see here, lambda is equal to 1.15 into 10 raised to minus 3, d is what value? 1 mm, that is what value? Minus 3 whole divided by 0.25. Then if you solve this value, lambda will get around 600 into 10 raised to minus 9 meter, or else lambda is equal to 600 nanometer. Wavelength of light used is how much? 600 nanometer. This is important numerical. Try to copy it. So remaining numerical will solve in upcoming classes. Thank you.